Welcome to the satellite communication course. Today we will continue the discussion of a Tdma terminal equipment. In that Tdma terminal equipment, we say that there is a terrestrial interface, and that for this terrestrial interface, input is from the telephone exchange, TV studios, or a data center. Now these are the input to your transmitter system. This is about transmission section, and same is about the receiving section here. This one is the receiving section. This one is the transmitting section. So now we have started with the transmission section, that is a direct digital interface equipment. In that direct digital interface, we have seen that input from your telephone exchange, or you can say that E1 carrier or a T1 carrier, that is the input to your system, that will be multiplexed, and then output of this DDI interface is nothing but a high speed data. Since your input data is a low speed, but output will be a high speed data. Now how we will get that high speed of a data? Because whichever the data input we are giving here to this DDI, so using this two buffer, one is use act as a read buffer and another is act as a write buffer. So alternately, data is available here from one buffer to the two buffer, second buffer. So that's why we will get that a high speed data that we have seen yesterday. And lastly, next we continue the discussion about a DSI here. So that is about a digital speech interpolation. In the digital speech interpolation, we have seen that it is it has a multiplexer, and that multiplexer is interfaces with this terrestrial interface component, and that is data from trunk exchange, and with the speed of with the rate of 2.048 megabits per second. Means input from this different trunk exchanges multiplex here, and we will get that a compressed data at the end, and that compressed data we are getting because of removing the whatever the pauses in the voice channels available. So now this is about your truncation. So we'll get that the output of this digital speech interpolation is nothing but the a compressed data, and that have the high data rate. Then we say that a system, a Intelsat system, they have a 240 input voice channel, and from this 240 input voice channels, so that output will be of a 120 DSI, or you can say that digital speech interpolation model. Now here that Intelsat use this a DSI technique to enhance the channel capacity, and we say that whichever the input signals we have, if we have the large number of voice channels available, so we'll get that a compressed output there. Now this example, if we consider that this one is about a even carrier, that is we can say that is about a two even carrier, and that two even carrier has a 32 PCM channels, so we can consider, and that 32 PCM channels have the rate of 2.08 megabits per second, and they are multiplexed, and will get that output at a rate of a 2.048 megabits per second, and that's why it's providing that 2 is to 1 compression because of this multiplexed output here. So we use a DSI system or a DSI in a Tdma system where a 2 PCM or oblique TDM streams are compressed to on a one stream. Or you can say that a 240 input voice channels we have that are compressed to the 120 DSI. That is about a digital speech interpolation technique. So that is about a part of a TDMA earth station equipment. So here we have a DSI, and then we can say that input from this TDI as well as input from the DSI, that will be multiplexed here. So we have seen this DSI. Now we'll continue the discussion with FDM SG coder. So FDM SG coder means what? FDM supergroup coder there. Now in this, we say that the input to this FDM SG coder, that is from the terrestrial input, terrestrial interface. So it's supposed to be considered that that input is from the trunk exchange or a telephone exchange to this FDM supergroup, and we supposed to be considered that there are the 12 analog channels or analog voice channels that are multiplexed with a this particular 12 SSB channels at a basic of a 48 kilohertz of a bandwidth there. And at a second level, so from this we will get that from the second level, we'll get that from this 12 SSB channel. So second level 12 into 5 means 5 basic groups are multiplexed here so that it provides a 60 SSB channel. 60 SSB channel at the rate of 240 kilohertz. So to transmit that particular a super group channel means these are nothing but because the 12 SSB channels are multiplexed with 5 groups, so that it forms a 60 SSB channel, and that is nothing but it forms a FDM supergroup code, or it forms a supergroups. Okay, this is nothing but a supergroup. When we transmit this supergroup signal through this TDMA system, so we can say that it requires a 240 kilohertz of a signal in the frequency range of what we can say 3122 to 552 kilohertz. So means we'll get that a digitized output using this particular coder. So now if you see here, so we say that a 12 SSB channel at 240 kilohertz means we have a 240 kilohertz of a signal in the frequency range of this one, and that will be digitized using a coder. So means that signal is nothing but what, it will be band pass at a 550 kilohertz frequency and quantized using this 8 bit per sample, and that will gives us that 4.416 megabits per second output. So means this particular signal we can supposed to be consider that it will be a sampled at a 552 kilohertz and quantized using this 8 bit per sample, and we'll get that 4.416 megabit per second. That will be the coder output. Now here we say that a analog FDM supergroup signal that will be coded, and that coded output is about a 4.416 megabits per second, and that will be applied to the a buffer. Means we can say that we have this 4.416 output, that is coder output, that will be applied to this buffer, and buffer is act as a compression buffer. The same concept earlier we have seen that one buffer will be act as a reading the data, another buffer is act as writing the data, and these are nothing but act as a compression buffer, and that buffer stores that samples in a TDMA frame. Now this particular stored data from this buffer 1 and buffer 2, and that will be out from this multiplexer. So we'll get that a TDMA bus data, or we can say that that bus data has a TDMA rate in that bus mode, because this data is read out from the buffer. Means in that case, one buffer is used for the writing the continuous data, and the other is used for the reading of data stored in this previous frame. So means what? Each buffer is in write and read mode in alternate frames, and will get that a high data rate. So that is about from the transmitting side. So similarly, we have a receiving side. So same components are there at the receiving side. So DDI, DSI, FDM, SG. So how it work for the transmission? Similarly, it will work for the reception. So on this particular receiver side, so these are the two buffers. Means these two buffer here in the transmitting side, this two buffer is act as a compression, but at the receiving side, it will be act as a expansion buffer. Instead of a compression buffer, because transmitting data, it will act as a compression buffer. For the receiving side, it will be act as a expansion buffer. And that FDM supergroup decoder will work to get that a analog signal. So whichever the bursts are there, they are written in the two buffers while receiving, and the two buffers are work alternate manner. So frames are alternate frames are writing in this particular buffer. So means we can say that one buffer is in data is written in the one buffer, and a previously written data in another buffer, that will be read out. That is will be that process is continuous process, and that will be the output to the FDM supergroup decoder, and then that will convert that data in the form of a analog data. Means generally that data is in the form of a digital one, that digital data will convert into the analog supergroup signal. So that is about a FDM supergroup coder. At a transmitting side, will get that high data rate because compression buffers are there. At the receiving side, this buffer will act as a expansion buffer, so that we'll get that a output, analog output that we require for this trunk exchange or a telephone exchange. So from this FDM supergroup, so that will transmitting side input from this, and from the receiving side output from this to this, in whichever the terrestrial interface component. Now then after this DDI and DSI and FDMSG, all these three, they are combined at this multiplexer. So this multiplexer combines the whichever the sub bus generated by this terrestrial interface modules. Now these are nothing but a terrestrial interface module. So that multiplexer role is what? It combines all these sub bus generated by this terrestrial interface module, and it also combines a voice order wire bits, and it appends that a preamble data from the preamble generator. This is about a preamble generator. So means multiplexer combines, as well as it also combines the voice order wire bits, voice order wire bits, and it again appends the, means it combines that whatever the preamble data from this preamble generator, and then it forms one particular data bus there. So we'll get the output that is that is about a data bus after this multiplexer there. And that preamble generally in the data bus, it is to be placed at the beginning of the bus in each frame. So that is about a preamble. Now we have seen that a TDMA frame structure. So we have a bus length or that bus. So in which we say that there is a preamble. So now here the preamble and the data. That is nothing but one particular data bus. And that is about your TDMA frame. So that's why you can say that here that preamble is placed at the beginning of the bus in each frame, and that entire bus is placed at the assigned location in the frame and transmitted at the frame rate there. So means we'll get that output bit of this particular multiplex from this whatever the terrestrial interface models are there, and that output is nothing but what? It is about a 2-bit symbol with a serial to parallel converter at this QPS for this QPSK modulator. Now this output of this particular output symbols from this multiplexer, that are nothing but what? We can say that these are nothing but a two parallel bits. Generally that two parallel bit streams, and that two parallel bit streams are called as a I channel and a Q channel. Now these are about, we can say that a 2-bit symbol. Output of this multiplexer is nothing but a 2-bit symbol, and these two parallel bit symbols or these two parallel bit streams, that will be called as a I channel and a Q channel here. And this output of this multiplexer is applied to a scrambler, and that scrambler will randomize the bits in the data. So now the for this particular scrambler, if you see here, so it has a unique word gate is the input to the scrambler. So scrambler is used here. It has a two purpose. One is about a energy dispersion, and again it is providing the clock components in the data for the clock recovery. And the role of what? It just provides the data bits for the clock recovery. So generally a TDMA format, if you see that TDMA frame format, so it has a preamble and a user data. So means in each burst in a frame, there is about a burst. It has the preamble and user data, and that is about a total frame. And So that frames are a repetitive pattern. When we transmit that data, that frames are nothing but a repetitive pattern, and that repetitive pattern they have some particular power spectrum of the data, and that power of those particular frequency components generated, or that particular data frame we say, so at the receiver that may exceed the maximum permissible level. So when that will exceed that maximum permissible level, in that case, so some data may contain a long string of the component, means whatever the data we say that they have the a string of a data. That string of a data, a string of that data is nothing but what? A consecutive form of 1 and 0 there. So means our data is, that data bit is in the format of a 1 and 0 there. And that means it has a pattern of a consecutive patterns of ones and 0 there. But that patterns generated, that patterns are not enough to recover the clock at the receiver circuit. Okay, means at the reception, so when we say that it Tdma frame format, when we are transmitting, so it has a data of a consecutive ones and zeros, and that ones and zero is not able to obtain the a clock at the receiver here. Means clock recovery circuit, whichever we are using at the receiver, and that patterns will not produce that particular clock recovery information. So now that's why that scramblers are used. So scrambler is used to solve both the problem of that clock recovery and that consecutive ones and zeros data will not be transmitted. So scrambler has a output that will be generated by adding a pseudo noise sequence to this particular data bit set. So now if you see that here one example of a 4-bit scrambler circuit. So these are about a flip flops here, and it will generate a scrambled data output. This is about a scrambled data output. And here is a modulative adder, and this one is about a modulative adder. This one is about a data input. So we have a scrambler circuit, it will get the scrambler data out. Means here it generate a pseudo noise sequence so that we'll get that a scrambled data output. So means scrambling sequence is nothing but what? We have the a sequence is generated, whatever the scrambling sequence is generated from your input from this flip flops, and whichever the we have this data input we are adding, and according to that we'll get that a scrambled data output. Means we can say that earlier here, because of that 1 and 0 format we are not able to recover the clock information. So that's why the scrambler will solve the problem of recovery of a clock information by adding the pseudo noise sequence to this data bit. This is about a data bit. So adding a sequence to the data, so that we'll get that scrambled data output. And this scramble, whichever we can say that a scrambler, that scrambler or that scrambling is started or scrambling begins for the data symbol following the unique word symbol. Okay, so now we need to learn about that again. We'll come back to this, whatever the frame bit we have. Okay, so if you see that we have seen that a bus length, and in that we have the CT, CR, BTR. So now this is about this BTR, bit time recovery. This one is about a carrier recovery. Then after that we have this unique word there. Okay, we have the unique word. Now similarly we have this a unique word pulse or unique word symbol, and that will be useful for the synchronization process. So means if that unique word or that unique word pulse is not there, so at the receiver synchronization is very difficult. Means at the receiver side, descrambler. You can say that here is a descrambler at the receiver side. So synchronization from this will be difficult. This is about a LUW. Okay, so this is nothing but a unique word here at this reception. So means we can say that a scrambler at the transmit side and the descrambler at the receiver side. So that will be start from this particular unique word. Okay, so we can say that a unique just like we can say that is about it will start with a some particular unique word, and you can see that here we have a 4-bit scrambler circuit, and in that particular 4-bit scrambler sequence, so it will generate a sequence with a 4-bit shift register here, and whatever the PN sequence, that will be a modulo to added with the data sequence, so that we'll get that a scrambled data output. Okay, so that is about a scrambler in the Tdma terminal equipment. Next about differential encoder, and we have this QPSK modulator. Now data we have that a output of this scrambler is applied to this a differential encoder, and the output of this particular differential encoder that will be applied to this QPSK modulator. And this differential encoding or differential, you can say that that encoder is used here to avoid the phase ambiguity at the receiver carrier recovery circuit. Okay, we can say that the role of this here differential encoder to avoid the phase ambiguity, the phase ambiguity at the receiver carrier recovery circuit. Okay, that is about the role of this differential encoder. So now after that, it will transmit that encoded output to this modulator. So it is about a QPSK modulator, and after modulation, the modulated IF signal is generated, and that signal is sent to this hybrid, and which combines this particular signal, that IF signal here. And if you see that this particular modulated output, and we have this input from this IA bus, so that it will be up converted. So like that is about to the transmitter. So now how is this a QPSK bus modulator work here? Just we say that we have this a QPSK modulator here. Similarly, we have this output at this. This is for the transmit side. At the receive side again, we have a QPSK bus demodulator. So we should know that how this modulator and demodulator work at the transmit side and receiving side respectively. So that QPSK modulated output, that is the IF signal, that will send to the hybrid, and that hybrid will combine the signal with the initial equation modem. That is about the output from this initial equation modem. So it will generate that IA burst, initial equation burst here, and that will be combined at this particular hybrid there. And then output of this hybrid is up converted. Okay, here that is about to up converted for this transmission. Okay, so means we can say that that will be transmitted, whatever the data bus is generated, that bus is generated, that will be transmitted here. And that this is about this Tdma terminal equipment is at the earth station. Okay, this is about the earth station. So that's why it is about the earth converted, and that will be transmitted to satellite. That will be transmitted to the satellite there. So now we have this encoder is used to obtain that whatever the error is there. Okay, so similarly we have at the receiver side, we have a QPSK demodulator there. So if you consider that in a satellite, they have the differential coding equipment to solve the problem of this page ambiguity. And again, we are sending that a unique word data, and that unique word through the scrambler for the clock recovery. So means we'll get that information about that page, as well as the information about the recovery carrier. Okay, carrier recovery. So means we are providing the information regarding the carrier recovery as well as the page here. So that is about at the transmitting side. And then a satellite will understand that whatever the information, and then it will decode it. But in the case of a receiving side, that signal is receiving from the satellite. Here from the down converter means what? From satellite. Okay, that is about the output from the satellite. Then we have again the hybrid here. That is about I bus. Okay, this one is about likewise here. So it will then we have the QPSK demodulator here. Okay, means signal received from the satellite. It has the RF bus, and that RF bus from the different station. Okay, so you can say that it is about a different station, or a different from the different transponders. Okay, likewise, that is about from the satellite, whatever the output we are getting, that will be use that output from the satellite to this QPSK bus demodulator through this hybrid switch. Now this, whatever the role of this particular QPSK demodulator here, it demodulate the data, and whatever the data is demodulated there, that demodulator must recover the carrier completely, as well as that must recover that page there. Okay, because we can say that is about a page and carrier here at the transmitting side. Similarly, at the receiving side, so decode that whatever the we have the demodulator we are using, so that demodulator is to recover the a carrier whichever the carrier complete information from each IF signal, and then that is useful for the generation of the recovery of the clock. So again here we have a decoder. That function of this particular decoder is to remove the phase ambiguity in the recovered carrier. So here it is about what? It avoids the phase ambiguity at the receiver carrier recovery circuit. Okay, that is about encoder. So similarly at the differential decoder is to remove the phase ambiguity in the decoder in the recovered carrier circuit. That is the role of the differential decoder. And the descrambler, that will remove the whatever the PN sequence added to the data earlier. That is just like we have used that a scrambler, and it added the PN sequence modulo 2 addition, and we'll get the scrambled data. But in a receiver side, a descrambling process, the descrambler is remove the whatever the PN sequence added to the data, and then and data that will gives to the a demultiplexer. So generally that a particular PN sequence we have considered that PN sequence generated at this particular receiver, and that is to be synchronous to the one generated at the transmitter there, and then that will produce the a symbols, and that symbols is given input to this demultiplexer there. So means that descrambler data bus are demultiplexed here to obtain that a sub burst of this terrestrial interface model at this receiver side. Okay, this is about descrambler output. We'll get the symbol here, output to this demultiplexer, and then demultiplexer produces that a sub bus, and that sub bus which are to be processed by the receiver side at that are the terrestrial models. Okay, and then we will get that a output from this. Okay, that is output input to this telephone exchange or whichever the input we have. So now other blocks we have here in this terminal equipment is about a bus synchronization, as well as we need to learn about that what are the initial equation modem. So now we consider that one by one initial equation modem as well as the bus synchronizer. Here is about unique word generator, is about the same here for the multiplexer or a demultiplexer. But you can consider here that a Tdma bus synchronization. So now how your data is to be transmitted, data TDMA transmission to the satellite. So here if you see that there are the four Earth stations. One is a reference station, station B, station C, and a station D. And there is about you have a satellite here. But in a satellite communication, when we transmit the data from the Earth station to the satellite or from the satellite to the transmission, so there is a long propagation delay. So that long propagation delay from what? From an Earth station to the satellite, and that will be about if supposed to be that satellite is used in a or this satellite is a geo satellite, it is in a geo orbit, then that propagation delay is about a 120 milliseconds. So this is about a propagation delay. That will be about a 120 milliseconds. Means from the Earth station, if you transmit the data to the satellite, so that delay is about a 120 milliseconds. So that is nothing but what? A Earth station transmit a data bus, so then it will arrive at this particular satellite, and they have the delay of a 120 millisecond there. So means that time required or a arrival time at this particular satellite, if you consider that is about 120 milliseconds, so approximately that particular time required or the data bus arrive at this particular satellite, it is approximately at a 60 Tdma frame of a 2 millisecond. Okay, 2 into 60, that is about a 120 millisecond. Okay, likewise. If one frame is of a 2 millisecond and we have a 60 Tdma frame of a 2 millisecond, and that can be transmitted by the Earth station. Okay, so that is about nothing but a delay here. So that's why we can say that whichever the stations we are using, Earth stations, so all the Earth stations that are used, that all the Earth station they have the different range of a satellite, because range equations, range means this to this, from this to this, that is about a range, distance from this station to the satellite, distance from this station to the satellite. So now that all this station, Earth station, they have the different range of the satellite. So that's why if that range is a different, so that's why that uplink delay will be different. Okay. Now these are nothing but the Earth station. We have the Earth station that will transmit the data to the satellite. This is just like a burst. Okay, we just say that it is about the information, or this is about a data burst for this reference station. And this one is about the another Earth station. This is about a station A. This one is about a station B. Earth station. This is about a transmitting data to the satellite. This is about a uplink. So similarly, station C and a station D. Now each and every Earth station, if you see that they are located at the different positions. So that's why that range equations for a distance from this Earth station to this satellite will be a different. If the distance is different, so that's why the delay, uplink delays will be different. So means we can say that data bus from each station would arrive at a different time on the uplink. So from this, because of that different distance there, distance different range equations there. So that's why there is a probability that the bus from the different station overlap on each other there. Okay, because different station transmitting the data, so that's why they may overlap the data there. Okay.